Well, hello everybody. So this is the second lecture of week 6, and today we're going to look at, we're going to move away from the idea of Bernoulli trials and look at other common continuous distributions. The first of which will be the Weibull distribution, which is actually sort of a generalization of the exponential, and the second of which in this lecture we'll look at the uniform distribution, which is perhaps the simplest of the continuous distributions. We're going to save the normal distribution and log normal to the first lecture next week. So with no further ado, our first other common continuous distribution is the so-called Weibull distribution. As I mentioned, this is a generalization of the exponential. It's actually a very common, actually the exponential itself is a very common lifetime model, and I used it in a couple examples in the previous lecture. Weibull is also a common lifetime model, particularly for problems where this system is either improving with age or degrading with age. So things like fatigue of metals, when you're taking a metal bar and you're bending it until cracks propagate through it and then it eventually breaks. So that's a situation where the material is degrading with time. There's lots of cases where systems degrade with time. Anything that involves mechanical wear and tear typically degrades with time. I would say systems that improve with time are a little bit less common. Maybe one good example of an improving system is red wine, for example. Although it's a little bit, you have to be a little bit careful with that because red wine will improve with time for a while, but you got to be careful that you drink it before it gets past its best, because after a while it tends to go back down the other way. And to model that, we need a more complicated distribution, one with maybe a third parameter that takes into account both the improvement for a while and then the unimprovement. Another example of systems that improve with time is concrete. Again, concrete takes, I would say concrete will typically take about a year to reach its full strength. Certainly it'll be about a month before it reaches close to its full strength. So it will improve for about a year or so. But anybody that's seen bridges in and around Halifax know that sooner or later it starts to go the other way around. So it's another system that improves and then degrades. And most glues, for example, are systems that improve and but even they will eventually degrade. Anyhow, the whole point is that the Weibull distribution has been found to be a pretty good model for these sorts of systems. It also has a very simple cumulative distribution function. Capital F of x is just 1 minus e to the minus lambda x to the power beta. So you can recognize here that if beta is 1, this is just the exponential distribution, right? The exponential distribution was just 1 minus e to the minus lambda x. So that beta equal to 1, exponential is a special case of the Weibull, or the Weibull is a generalization of the exponential. Okay, well, if this is the CDF, we can get the probability density function by differentiating the CDF, and we get this this expression on the right hand side, a little bit more complicated looking. I think this is the version that's given in your summary pages, but I've rearranged it a little bit here to get. We've got a constant here, beta lambda to the beta, so that's a constant, and x is up to the power beta minus 1. So basically I've taken the x here, which is beta, and then subtracted 1 here. So x to the beta minus 1, and the whole thing is multiplied to e to the minus lambda x to the power beta. This is valid for x greater than or equal to 0, just as we had for exponential. It's non-negative distribution. The reason I wrote it this way is that it gives us some idea of the shape of the probability density function. When beta is equal to 1, we get x to the 0 here. And in fact, 1 here, lambda e to the minus lambda beta is what we get, and that's the exponential distribution as we are familiar with. Okay. But when beta is less than 1, the power on x becomes negative. We get, so suppose beta is half, then we get x to the minus a half. And when x is 0, then we get 1 over square root of 0, which blows up. It goes off to infinity. So when beta is less than 1, the distribution shoots off to infinity here, but decays more rapidly towards the right. What that means is that when beta is less than 1, we got a lot of early failures. And so basically we have early failures and less failures later. That means this is an improving system. On the other hand, if beta is bigger than 1, we got a positive power on x here. And so when x is 0, this function is 0. So that the probability density function when beta is bigger than 1 has this shape. We know the area still has to be 1, and basically when x is very large, this thing takes over and it goes back down to 0. So it has to start at 0, goes up, and then comes back down. And basically what that means is that we have very few failures early on, but more failures later on. And so this is a degrading system. So basically this beta can be used to model not just constant failure rate systems, which is the exponential, but also alternatively systems that are either improving or degrading. And like I said, probably most commonly in engineering, it's the degrading systems that we model. So let's illustrate this with an example. And this example sort of shows you also the kinds of questions that I would ask if I'm talking about the beta distribution. The time to leakage failure in a certain type of dry cell battery has a Weibull distribution. I'm sorry, I think I said beta distribution, but I'm really talking here about Weibull distribution, and beta is one of its parameters. And beta is equal to half for this dry cell battery. We also know that only 19% of the batteries last 5516 or more hours without leakage. What is the median time to leakage failure of these batteries? Okay, well, one of the things that I will rarely do with a Weibull question is give you both lambda and beta, because basically once you know that, you know the cumulative distribution function, and you can pretty well answer any of the questions very simply. So usually it's a little bit more tricky than that. I've told you what beta is, but I haven't told you what lambda is, but I've given you some other information here that will allow you to find the value of lambda. Okay, so let's start this question by defining the random variable. So let's let x equal the time to failure of the battery. So that's basically the time to leakage. And then we are told that x follows a Weibull distribution and the parameter beta is equal to a half. I.e., my cumulative distribution function is 1 minus e to the minus lambda x to the beta. If beta is a half, that means that this is equal to 1 minus e to the minus square root of lambda x. So that means we still need to find lambda. And if we've got another unknown, we'll need another equation to solve for it. We are told that, if we look up there, 19% of the batteries last 5516 or more hours without leakage. So the time to failure, the probability the time to failure is greater than 5516, we know is 19% or 0.19. And that this is greater than, I can write that as 1 minus f of x evaluated at 5516. Now f of x is this thing here, and so 1 minus that is just going to be that last bit. So basically we have e to the minus square root of lambda x is equal to 0.19. We know x is 5516 coming from this part of the problem. So now I'm just solving this thing for lambda. Take the logarithm of both sides. I got minus square root of 5516 lambda equals the ln of 0.19. I could square both sides and then divide by minus 5516. And that gives me square both sides. Then I got to put a minus sign on this side. Then divide by this. Okay. No, do the minus sign first. Bring that over to this side. Then we square it. Okay. So lambda is equal to brackets minus ln 0.19 quantity squared. That doesn't really matter actually for this particular problem, but it would if the beta was something else. The logarithm of 0.19 is negative, so we got to put the minus sign here so that we get a positive. Okay, because we know lambda has to be positive. Okay, then we get lambda is 0.0005, which is actually equal to 1 over 2000. Okay, so we're asked to find the median time to failure. Well, we know the median is the point x tilde, such that the probability that the time to failure is less than x tilde is a half, or equivalently, the probability that it's bigger than x tilde is also a half. If we use this version, then the probability that x is bigger than this is just e to the minus lambda x tilde. The probability that it's less than is 1 minus, so it's a little bit more complicated. So I just use this version here. So I got e to the minus lambda x tilde is equal to a half, and I just now have to solve that for x tilde. Okay, and then I plug in all my various bits and pieces, and I get the median time to failure is 960.9 hours. Okay. Okay, so the next common distribution is the uniform distribution, and as I mentioned, this is perhaps the simplest of the continuous distributions. All possible values in this distribution are equally likely, and the picture of the probability density function is just flat. But it has to be flat. We know that the area under it still has to be 1, so it has to be flat between two bounds, and these are the upper and lower bounds of the distribution. So the uniform is actually a little bit more complicated than it seems. Although it's equally likely on some range, it also has the range part of it. So you got to be a little bit careful with that. In other words, f of x is equal to, well, if this area is 1, then the height of this must be 1 over the width. And the width is beta minus alpha. Okay? So f of x, little f of x, is 1 over beta minus alpha if x is between alpha and beta, but 0 everywhere else. Okay? So that's the complete description of the uniform distribution. Main characteristics, the mean, of course, is the balance point, and we know that this is a symmetric distribution about the midpoint, so the midpoint must be the mean, because that's where it would balance. Okay, so that's just the average of alpha and beta, 1/2 alpha plus beta. To get the variance, we have to integrate f of x times x squared over the range, and if we do that, we'll find that the variance of x squared is, the variance of x is 1/12 the width squared. Okay. So let's look at an example illustrating the uniform distribution. If we look at the Fortran programming language, most compilers have a function called rand 0 with an argument which is typically 0. Then this returns numbers which are uniformly distributed between 0 and 1. If xi is assigned subsequent values returned by rand 0, and we let y equals the sum of these xi's of 12 of these xi's minus 6 and all multiplied by y, then what is the mean and variance of y? We'll assume that the numbers returned by random 0 are independent, and if it's a half-decent random number generator, this is at least approximately true. Or at least it's usually closely true. We know that each xi is uniformly distributed between 0 and 1. I've written it this way, by the way, and it just means that 0 is a possible value, but 1 is excluded. But we can get arbitrarily close to 1. So you can have 0.999999 or whatever. So it doesn't really matter to us that we have that we talk about whether we're excluding or including the endpoints. So basically our range, our bottom end is 0, and our top end is 1. So alpha is 0, beta is 1. Sorry. And that means that our distribution looks like this. Let's do it in black. So our distribution looks like this. 0, 1. And this is fx of x. And this height is 1. So that the area the area under the distribution is 1. Okay, so the balance point is the midpoint, so the mean of this distribution is 1/2, so that's right in the middle here. And the width is 1, so the variance is 1/12. So we're looking for the mean and variance of this sum up here. Y is equal to alpha times the sum of 12 of them minus 6. So let's say, okay, the expected value of y is the expected value of the right-hand side. So expected value of alpha times the sum of the xi's minus 6. Well, this is good. The alpha is constant, so I can bring that out in front of the expectation. And then I get the expected value of a sum, so I can break, which is the sum of expectations. So I get the expected value of the sum of xi's minus the expected value of 6. Well, 6 is a constant, so it's expected value of 6. The expected value of the sum of xi's is just the sum of the expected values, and they all have expectation 1/2. Well, there's 12 of them. So 12, a half plus a half 12 times gives me 12 times a half. Of course, that's 6. Minus 6 gives me 0. So the expected value of y in this expression is just 0. The variance of y is the variance of the right-hand side, the alpha times the sum of the xi's minus 6. The alpha can come out front. This is the variance, so it's squared. And then I get the variance of this sum. I could look at it first as the variance of this plus the variance of this, if they are independent. Well, the 6 is independent of everything else. It never changes for anything. So they are independent, but the variance of 6 is 0, because 6 is a constant. So that term disappears. So then I'm left with alpha squared times the variance of a sum. And if those terms in that sum are independent, then the variance of a sum is the sum of the variances. And they are. We've assumed that they are independent. So this becomes alpha squared times the sum of the variances of x. And each of those are 1/12. There are 12 of them that I'm adding up. So I got 1/12 plus 1/12 plus 1/12, 12 times, which gives me 12 times 1 over 12, which of course is just 1. So the variance of y is governed by this parameter alpha. So alpha is actually the standard deviation of y. And I think that is it for the uniform and the Weibull distributions. So next day, tomorrow, I guess we'll be, in the tutorial, in any case, we're going to be doing some examples illustrating these distributions. Okay, so that's it for today. I'll resume with week 7 material next week. Thank you. Bye-bye.